An important classification of space groups is in two types called symmorphic and non-symmorphic. So, we will look at this classification in this video. So, we define symmorphic operations. So, and symmorphic operations are rotations, roto-inversions or lattice translations. So, as you know, rotations can be a n-fold rotation, where n is equal to 2, 3, 4, 2, 3, 4 and 6. Of course, you can count one fold also, but that is an identity. Similarly, roto inversions, you have n bar axes of type 1 bar, 2 bar, 3 bar, 4 bar and 6 bar. And then you have lattice translations. So, lattice translations you can write as the basis vector defining your unit cell and linear combinations of these. So, you can write Na plus Mb plus Lc, where NML are integers. Of course, if you have centered cell, then some of the fractions are also allowed, but we are taking only the lattice translations, either with fraction in the case of centered cell or only integers in case of primitive cell. So, here I have given you what will be true for primitive cell. None of these translations involve non-lattice translations. So, the symmorphic definition requires that they do not involve any non-lattice translations. So, those operations we call symmorphic operations, rotations, roto-inversions and lattice translation. Please keep this in mind that it has to be a lattice translation for symmorphic operation. Non-symmorphic operations, we have discussed this in some of the previous videos, are two types, screw and glide. Screw, as you know, there are 11 different kinds of screw. Let me begin with 2. So, 2 1, then 3 1 3 2, then 4 1 4 2 and 4 3, and finally 6 1 6 2 6 3 6 4 and 6 5. These are the 11 screw axes and operations associated with them. And then there are glides which have the symbol A, B, C, these are axial glides. Then you have D, the diamond glide, E, the double glide, and N, the diagonal glide. So, we have discussed these operations. These operations always involve some non-lattice translation. For example, glide involves half the lattice translation. So, half lattice translation is not a lattice translation. So, they involve translations. So, for example, A glide will involve a translation by half A. So, all operations which involve non-lattice translations, and there are of these two categories, screw and glides, are called non-symmorphic operations. This is what is used in defining the symmorphic and non-symmorphic space groups. So, when we define symmorphic space group, we define them as space groups that can be generated using only symmorphic operations. So, that is very important. I have already written generated in capitals and in a different color. I am further highlighting it by putting it in a box. That is, this word is important. Space groups that can be generated using only semorphic operations. That is, they will involve, they can be generated only using rotations, roto-inversions or lattice translations. They will not involve as their generator screw or glide. I emphasize that generated is important. Sometimes there is a misconception that semorphic space groups do not contain screw or glide. That is not true. They may contain screw or glide, but screw glide are not required, screw and glide operations are not required as generators. They can be generated purely by semorphic operations. We will see this will become clearer when we look at some examples. Now, let us look at Hermann-Mauguin symbols. So, in the Hermann-Mauguin symbols, one of the characteristics of Hermann-Mauguin symbols is that they give you all the generators, all the essential generators of any space group. So, the Hermann-Mauguin symbol itself is a collection of generators, and since semorphic space groups do not require non-semorphic generators, they do not require screw and glide as their generators. In the symbols of semorphic space group, there will be no screw or glide operations. So, they will contain only semorphic symbols. So, some examples, some of the simple examples are, for example, P2. So, you can see 2 is a two-fold axis, is a semorphic operation. C2 again semorphic operation. MMM, the mirrors are semorphic operation. So, and these are the generators of these group. So, once these symbols are known in Hermann-Mauguin symbol, we can generate the entire group just using this information. There are 73 semorphic space groups. We will devote another video to the listing of the 73 semorphic space groups. Let us now define the non-semorphic space group. So, by contrast, semorphic space group was defined as those which can be generated only using semorphic operators or semorphic operations. Non-semorphic space group in contrast is defined by those which will require non-semorphic operations as their generators. So, they cannot be generated only by semorphic operations. So, they not only contains non-semorphic operations, they also require those non-semorphic operations, the screw or glide as their generator. So, obviously, since the Hermann-Mauguin symbol as we saw contains the generators of the space group, the symbol will contain symbols for screw and glide symmetry. So, it is very easy to identify from the symbol itself whether the space group is semorphic or non-semorphic. If you see a screw axis in the space group symbol in the HM symbol, then it is non-semorphic. So, here there is a 2-1 screw. So, non-semorphic, a C glide non-semorphic, NNN non-semorphic. So, these are non-semorphic operators which are required as generators. Another interesting distinction between the two groups, two types of groups, semorphic and non-semorphic, is in terms of the site symmetry. Now, by site symmetry, as you know, we mean symmetry, point group symmetry of a particular site, not the point group symmetry of the entire crystal, not the point group symmetry of the space group, but point group symmetry at a site, at a given site, means what symmetry operations are actually leaving that particular site invariant, that particular site fixed. So, if you look at from this point of view, then Symmorphic space groups has points with site symmetry the same as the point group of the same space group. So, every space group has a point group and every point in the space group, every point in the space has its own site symmetry group. These two need not be equal, but in the case of symmorphic group you can find some sites. All sites will not have this property, but you will have some sites which will have the same point group as the space group, and non-symmorphic space group this property is not true. So, there are no points with site symmetry the same as that of the point group of the space group. So, again this will become clearer when we take the examples. So, we now look at some of the simpler examples, very simple space groups. So, for example, I am taking a space group number 3, as you can see it is one of the very early space groups in the table of 230 space groups, and this one is a monoclinic space group, monoclinic crystal system. So, that requires only a two-fold, as you know, and you can see from the Hermann-Mauguin symbol that this has a generator just a two-fold. So, P stands, the capital P stands for primitive lattice. So, that means the lattice is primitive. So, I have drawn the unit cell in the projection. This is a B is perpendicular to the projection plane. So, let me fix this labeling. So, this direction is A. So, this the direction coming down, slanting down is C, the direction parallel to the horizontal direction on the page is the direction of A vector, and O is the origin. So, this is the projection of the unit cell. The B axis is taken to be perpendicular to the plane of the projection, and B axis is taken to be the two-fold axis. This is called the B setting, and this is what is taken as a standard setting for monoclinic. Although of course, you can make your two-fold parallel to the C axis, or you can make your two-fold parallel to the A axis, but those are not common, not so common, and it is preferred to keep the two-fold axis parallel to the B axis. So, if we now using this two-fold information, if we start putting the two-fold at a lattice point, then obviously I will get two-fold at all the lattice points, because all lattice points are equivalent. Now, let me try to put a motif in a general position. The two-fold will rotate it 180 degree. So, we will create a motif somewhere there. I write a small plus there to designate that it may not be exactly on the AC plane, but may have some height of plus y, let us say. So, this is above the AC plane. So, these notations you are of course familiar. Now, since all lattice points are equivalent, you will have identical points, identical pair of points at each lattice point. So, that completes the general position for these two folds at the corner. But you see that because of these positions now, there are two folds already in between. So, for example, this two-fold is relating these two objects in this way. and of course it will relate all other objects. I don't want to draw all the lines, but these two also you can see are related by that twofold. So, there is a twofold which comes in between. This property we are familiar when we were looking at the plane groups also, that whenever you have twofold axis passing through a lattice point, then in every translation direction there will be another twofold axis at half the translation. So, similarly you generate a twofold at c by 2 there, a twofold here and a twofold here. And note that the diagonal of this parallelogram is also a translation, lattice translation, that is the A plus C translation, and there also the same principle will act and you will get a twofold in the center. So, these two folds all get generated by our starting twofold. If you look at the point with highest symmetry, remember Wyckoff letter A always gives you a point of highest symmetry. So, according to the international tables, the point of highest symmetry in this is a point with site symmetry 2, that is, it is on a twofold axis and coordinate 0 y 0. If you look at that, so 0 along A, y along B. So, it is actually this special point by the circles which I showed you initially, those were the general points, but now we are talking of a special point and I am showing this, let us say, in some other color, or maybe black was better. Yeah. So, so this black dot is representing this a special point 0 y 0. Now, if I try to create equivalent positions for this, you can see that unlike this open circle which got rotated by 180 degree and gave you another equivalent point, this will rotate on itself because it is on the rotation axis. So, it will not create any new equivalent position. So, that is why it will remain where it is and its site symmetry is 2. Hermann-Mauguin symbol gives you the point group of the space group, and the method of determining that is to simply forget the letter symbol, the centering symbol, and convert any screw or glide to the normal rotation and mirror plane. Here that is not required, we do not have a screw and glide. So, the point group of the space group is 2, and you can see that the site symmetry of this location of Wyckoff location 1A, generally Wyckoff locations are named after by combining the multiplicity and the Wyckoff letter. So, I will call this site 1A. So, site 1A has site symmetry 2, the space group also had the point group symmetry 2. So, this is what I meant when I said that has points with site symmetry the same as the point group of the space group. Now, C 2 is another interesting example, but by the letter C we mean C centering. C centering means the AB face. So, I have lattice points at the corners, but I have additional lattice point on the AB face, which on the projection is there and it is on the center of the AB face. So, it will come there, and since it is on the center, in the projection it is coming there, but these will have a height half in the y direction. So, you have 2 additional lattice points on these two faces at half the y height. So, that is what will give you the C centering. But then I again start generating the space group symmetry. So, I put the two folds, at the lattice point. Now, the lattice point is on the centering face also. So, we get a two fold there as well. And we have seen that at half positions also you will get so you get these two folds. Now, again if I start putting my motif positions. So, in a general position I get these just like I had got in the previous example. But now, the center of this edge here, this was also a lattice point because of the C centering. So, I will have to place identical motif there also, but that is at half height. So, I will get a pair of points half height in the B direction, but they are at, I will write half plus to indicate that they are at half height. Let me get rid of some of these. Similarly, for this face centering, now an interesting thing happens that you can see now, that because of these half positions you find that you have actually introduced, now I have too many reds, so let me use blue for this purpose. You have actually introduced a screw axis at these locations. So, if you take any point, let us take this point, and you rotate by 180 degree, so it will get there, but then you translate by half. So, you can see this was just plus, so it was plus y, whereas this is half plus, so this is half plus y. So, you have a y translation of half relating these two. So, there is a screw axis there. Similarly, if you look at these 2 points now being connected, so you rotate by 180 degree and translate by half. So, several screw axes get generated between these red two folds. I do not have to create any new position. The positions which were created by the pure two fold also automatically gets related by these screw axes. So, these screw axes get generated by the action of the two fold and the translations. So, this is a generated screw axis, but they are not essential. Because you can see all the equivalent positions I could generate only by the pure two fold. So, that is why this is not a generator. So, in the space group symbol, we are only using C2, the pure two-fold, which shows the generator. Again, if you look at the location now, the work of location 2a, so it has a multiplicity 2, multiplicity is 2 because of the C centering now, because 0 y 0 also gets replicated at half y plus half 0, because you have half 0 as your centering translations. So, any position will also have another equivalent position if you add half 0. So, 0 y 0 and half y plus half 0 gives you the two coordinates to justify the multiplicity 2. But what is important, that if you see the site symmetry 2, and again C 2 will give you the point symmetry 2, and these two are equal, indicating another property of the symmorphic space group, that this is a C 2 is also a symmorphic space group. But I gave you this example to show that this is a symmorphic space group, but it still contains non-symmorphic operations, it contains screw axes. So, as our final example, we take this P21. So, here the two-fold screw itself is the generating operator. So, I put it on the lattice points, let it pass through the lattice points. It is again a P lattice. So, there is no centering translation here. So, I get these screws. So, compared to the, with respect to these screws, if I now put the equivalent positions. So, if this is plus y, this will be half plus y, because of the screw translation of half. All lattice point will have identical set. But now again you see that just like between two two-fold axes, we found that another two-fold was get generated. Between two screw axes also you are seeing that another screw axis is getting generated, because these 2 points, for example, you can see are related by this screw. So, I can add all these additional screws, but here there is no pure two-fold, only screw axes. So, for the generation of a space group, that screw symmetry is required. So, the Hermann-Mauguin symbol has this screw operation as its generator, but if you find its point group, so by the method of finding point group, we cancel the letter, but we also convert the screw axis to simply 2. So, the point group of this space group is also 2, but the highest site symmetry in this case is just the identity. Site symmetry is 1, that is, there is no point in this space group which remains fixed by any symmetry operation other than the identity. That is because in the two-fold case, in the pure two-fold case, points on the axis were invariant, but in the case of a screw axis, even points on the axis are not invariant, because the rotation part will leave them invariant, but when you translate by half, the point will move up or down along the axis. So, there is no point which has a two-fold rotational symmetry as its site symmetry. So, the point group of the highest point group or point with highest point site symmetry is simply 1, whereas point group of the space group is 2, and these two are not equal, indicating that this is a non-symmorphic space group. Thank you very much for your attention.